Okay, I think we can begin. We have a lot of code to go through. And thank you for coming. My name is Vittorio Romeo. I work at Bloomberg. And today I'm going to show you my experimental implementation of zero-allocation and node type erasure features. So I'm going to sit behind the podium, not because I'm shy, but because I have the technology of JavaScript, and I can move a virtual laser pointer and line highlighter on my screen. And that would be helpful when you see a lot of template code. So what we're going to do today is learn how to build chains of asynchronous computations. And if you don't know what that means, think in terms of future composition. And we want to avoid using type erasure and dynamic allocation. And a way we can do that is by using a lot of templates. And as a sneak peek, this is what we're going to implement. We're going to have some sort of system that allows us to express chains of computations. For example, this leaf over here that returns hello, and then we can compose it with a continuation that, given hello, appends world at the end. And what this is going to do is going to return hello world, and we are encoding all the information about this graph as part of the type system. So you can imagine that it is a sequential node where the first node is a leaf taking void and executing the first lambda, and the second node is another leaf taking SED string and executing the second lambda. So this is the approach we're going to use. If you know about expression templates, this is pretty much it, but for SED futures and asynchronous computations. And another example, we can do something a little bit more complicated. Let's say we want to execute two computations in parallel, for example, two HTTP GET requests. We can have this all node over here, provided with any number of computations. They will be executed in parallel, and then we can attach a continuation at the end, which in this case will take a tuple as its argument so that we can access both results at the same time. And in this case, the type of the graph that we're going to produce is a sequential node where the first computation is this parallel all node that executes two leaves at the same time, and then invokes this continuation, which takes a tuple with the results and executes the second lambda. So feel free to stop me anytime during the talk, and if you have any question. And I also have a lot of interactive one-box examples that we can run if you want to see how everything works, and we can play around with them. So let's begin from the beginning. I hope that all of you are familiar with SED future and async. Can I have a show of hands? OK, that's pretty good. So future and async were introduced in C++11, and what they do, they allow you to model asynchronous tasks, and they are quite useful. And one of the most common use cases is just spawning multiple tasks running in parallel, for example, F0, F1, and F2. We're going to use async, and with a launch policy that runs it on a separate thread. And what we're modeling is basically this graph over here, where all of them are running at the same time, and eventually they will block at the end when we want to obtain all the results of the tasks. However, as soon as you have something more complicated, like this dependency graph, for example, we want to run F0, and as soon as F0 is done, we want to spawn F1, F2, and F3 in parallel. Then we want to aggregate the results in S4 and also spawn F5 at the same time. It becomes really complicated to use just future and async to express this. If we think about sequential composition, what we're actually trying to do is nest async calls. So if we have this simple graph over here that has F0, and when F0 is done, we want to execute F1, one way we could express it without any additional abstraction in C++11 would be to first start the first node with async, have some behavior inside the node of what we want to execute, and when that is done, we will start a new future with async that continues on from the result of the first one. Obviously, there are different ways you can do this, but the point is that there is no abstraction, no .then in C++11 that allows you to express that intuitively. Another even more difficult task to achieve with async and future is collecting multiple futures into a single one and basically expressing the idea of when all the futures AX are completed, then we want to execute B0. And in this case, you can imagine some sort of fork join model where we have A0, A1, and A2. And when all of them are done, we're going to aggregate the results and invoke B0 as another future. Now, you can do this in multiple ways. This is a very horrible way of doing it, but the idea is that you have to manually spawn these three futures somehow, then either wait or attach a continuation to those three futures at the end, And once you do that, you can finally aggregate the results and spawn your final node as a continuation of the previous one. So as you can see, there is no way in C++7 to do this cleanly without additional abstractions. So what do we want? We want intuitive abstractions that allow us to express future composition. And there is a proposal, a TS actually, extension for concurrency, that is attempting to standardize these abstractions under the form of when all, when any, and .then. And those will be part of SCD experimental future if you have a compiler that supports them. And we already have these things in Boost Future. As long as you define some macros at the beginning, they will expose .then, when all, and when any for you. And this is what we're going to use in some of our examples. Also, last year here at ACCU, Anthony Williams gave a really, really good talk about concurrency, parallelism, and coroutines, covering not only the extensions for concurrency TS, but all the upcoming additions to the standard library. And I strongly recommend it if you are interested in the subject. All right, so this was our previous example. We have F0 and then F1. If we use the Boost experimental extensions, what we can say is simply Boost async, launch async, hello, and then this will return a future, and we can attach a continuation to the future by simply saying .then, providing a lambda, which will accept the previous future as an argument so that you can obtain its result or its exception in case of failure. And then we can attach extra logic to the end of the composition. And in this case, we can just print out hello world. Similarly, when we want to express the fork join paradigm, what we can do is simply use boost when all, which is a variadic, it's a variadic function that takes any amount of futures, and they will be all executed in parallel, and when all of them are done, then the continuation that we attach at the end will be executed. So this is a very clean way of expressing this kind of parallelism. So my point is that abstractions like then, when all, and when any allow us to express this kind of composition very intuitively. And as you can see, what they do is they take a future or a callable object, and they always return another future that you can compose further. So you can build your graph out of these convenient abstractions. So if you see, for example, this small code snippet over here, where we have some future that takes an int, returns an int, a, and we initialize it with async or whatever, and another future b, which is attached to a as a continuation, you can see that when we call .then, the return type is another boost future. And what this implies is that type erasure is happening under the hood because we are storing everything into the same type, allowing composition, but we are erasing the real type of the lambda over here that we provided. So we are hiding the concrete type of this callable object behind future. Additionally, what future does is using dynamic allocation to keep track of the share state. And those two things, type erasure and dynamic allocation, are not free. They have a runtime cost, they have a memory cost, and the goal in this talk is trying to play around with an experimental design that attempts to remove that additional overhead of type erasure and dynamic allocation and try to measure if it's worth the pain. So an alternative design. We need type erasure because, let's say, there are some places where you can't really avoid type erasure. If the shape of your computation graph depends on runtime control flow, so maybe you want to attach a .then if some condition is true, maybe you want to attach a when all, then you don't really know at compile time how your graph will look like. And that's where you need type erasure because it's obviously something that a compiler doesn't know in advance. However, if the shape of your future graph, so if you know exactly how the shape looks at compile time, then what we can do is encode that as part of the type system. And this is the approach I will take to avoid type erasure. If you're familiar with expression templates, this is basically it applied to SCD future. So imagine we have this kind of design. We use auto everywhere because we don't know the type. We want it to be deduced from the compiler. And we begin our graph by creating a leaf node, which stores an arbitrary computation. In this case, it's just printing out a character A. And then what we do, we can attach a continuation to F0, which will store another arbitrary computation, in this case printing out B, and name that F1. And now we're using auto because the types of F0 and F1 are really complicated and they will just keep getting bigger and bigger. In the case of leaf, what we do is simply take something in the constructor, any callable object, and then store it as part of the type of leaf. And if you're wondering why there are no template arguments here, this is C++17's class template argument deduction, and we're going to see it in a few minutes. In the case of the then continuation, what we do is return this sequential node, which takes two nodes as template parameter, A and B, and what it does is simply says, after A is done, I will execute B. And in this case, what then does is simply take an arbitrary computation as its argument and put it in a leaf for you and return the sequential node that executes the first leaf and then the second leaf. So as you can see here, the type of F0 is just a leaf of a lambda. The type of F1 is a composition stored in a sequential node of the first leaf and the second leaf. Does that make sense? Similarly, when you have when all, for example, and you just want to run a bunch of computations in parallel, what you can do is return a new type of node, maybe a parallel type of node that contains an arbitrary number of leaves. In this case, when all is simply a variadic template function that, given an arbitrary number of closures, it will stick all of them inside a parallel node wrapped as leaves, and you will be able to continue your composition on the special type. So the type of F1 in this example will be a sequential node of a parallel node containing a bunch of leaves, and whose continuation is the final leaf that prints out B0. So we can avoid type erasure simply by encoding the structure of the graph in the type system. But what about dynamic allocation? So first of all, SED_future T uses dynamic allocation because it has to provide a share state for the eventual result and exception. And also it might use that same share state if some additional synchronization primitives are required to synchronize abstractions such as when all and when any. So if you need to keep a track of a counter or need to know if any of the computation is done, the share state might be a good place to store additional information. So this is an example of how it may work. We have the promise, which is the producer for the value of the future. And then we have the future, which is the abstraction from which you can consume the value produced by the promise. And you usually instantiate a promise, get a future out of it, and then use the future or attach a continuation to the future. But the key point is that both the promise and the future refer to the same share state that could have some sort of reference count to keep track of whether or not the promise and the future are still alive, and a variant of value of exception to keep track of the result. So there is this indirection and dynamic allocation required to make this model work. So my alternative proposal is, what if we simply store the state in place inside the final graph object? You know, we are composing this graph, we're going to get a giant type, there's going to be an object. Why don't we store all the things we need inside the type on the stack? And while this works, it adds an extra requirement on the usage of this kind of future composition, which is that the graph object must be kept alive until execution is completed. Because now the things are on the stack, we cannot use reference counting, but we need the user to guarantee that the object will be alive until all the asynchronous combinations are done. So in this case, imagine we have this graph type, which is just a composition of all the nodes, and inside it, we might just store the state, which contains either a value or an exception at the end. So as an example, we've seen before that we have the when all primitive that just returns a parallel node, in this case of leaf A and leaf B. So what we could do is store our share state over here in the parallel node that just has some atomic counter that keeps track of how many futures still needs to be executed, in this case 2. And then we can store the leaf A and leaf B still inside the same parallel node, and leaf A will have its own result, leaf B will have its own result. They will know about the counter will be decremented every time one of them is finished, and when it reaches 0, we can proceed with the continuation and obtain the values out of the leaves. So all you see in this graph over here, in this diagram, is on the stack in place inside the object which is returned by the last composition of the computation graph. All clear? This is a slightly more complicated example. We could have a when any, A and B, and when all of that when any and C, then we execute D. So you can see this can be nested arbitrarily. When any might use a Boolean to know whether or not any of the leaves is done. When all will have its own counter and the other leaf, and the sequential will have the entire when all computation plus the leaf that's the continuation. So everything will be on the stack, will be a very big object containing the state that we require. So yeah, I want to reiterate this point. If we have a feature like this one, where we have when all and when any, it's not really deterministic when it will be done. It depends on the kind of executor or schedule that we use. It depends on which one finishes first. So if, for example, we have a completely asynchronous scheduler that maybe just detaches threads for each computation, then this call over here, scheduler.execute, will be asynchronous, will be non-blocking and return immediately. But now it's on the user to make sure that the F object lives long enough for the computations to finish, because they still need to access the share state inside on the stack. So we do have ways of doing that cleanly, but the main point that this is a restriction compared to what you can do with STD Future. So as a recap, we can avoid type erasure by using this kind of expression template thing, so encoding the entire graph inside the type system. And we can avoid dynamic allocation by simply just storing the share state in place inside the object, with the restriction that the final graph object must outlive the execution of all its nodes. Yeah, sure.
Go back one slide. So what I'm wondering, if you have here a when any on A and B, and then let's now say that, like, for example, B takes like a lot longer than the whole rest of the computation, then you have the problem that you need to keep the state alive even though you actually have the final result of the problem.
Yes. So the question is, in this case, I have when any here, and maybe A finishes immediately, but B takes a long time in the background. So what do I do? Do I keep the state alive for longer? So when any is a very difficult beast to implement, especially with this structure over here. So what I managed to do for this implementation, and we're going to see later if we have time, is to continue as soon as possible from the first computation that finishes, but all of the other computation will run in the background. So in this particular case, I keep it alive until everything is done, but you can get the final result early asynchronously. Note that this restriction seems very harsh, but there is nothing preventing you from simply allocating the whole graph on the heap and then managing it in a different way. So you can still do things that you would be able to do with STD Future. You just need to kind of change your way of thinking a little bit. However, one thing I want to do in the future is implement automatic cancellation of the things that when any should not continue from, so that's under experimentation. Any other question on the design so far? Because now we're going to dive into a million slides full of template code. All right, so we'll start by implementing the leaf node, which is the simplest one, then sequential composition, when all composition, and these three things will be just stateless closures. Afterwards, we will implement return value propagation, so we will be able to accept values and return values from the nodes. Then we will have blocking execution, which basically prevents the graph from going out of scope until it's completely done. And then we will implement the continuation style syntax. And if we have time, we're going to take a look at the any node, which is the tricky bit. First of all of these nodes must have something in common. And I think there is a concept here, a node concept, which is quite simple. All the node types have to do is expose a single member function that's called execute. And what execute does, it accepts a scheduler by reference. So if you've seen Detlef is a very good talk, this could be an executor, for example, that just tells you how to execute this particular node. And execute also accepts a then continuation. And the idea is that since nodes can be executed asynchronously, such as when any, we need to provide the continuation as a callback because we don't want to block until the whole node is completed. We want to execute as soon as possible. And the idea is that we execute the stored computation in the current node through the scheduler and then asynchronously continue execution with the then argument over here. You might also notice that it is L-value ref qualified because the node must be kept alive and it doesn't really make any sense to call execute on a temporary node. If you're still confused about the scheduler, an example can be a simple callable object that whatever computation you give it, it simply calls the cd thread of f.detach. So that's a very simple, not really smart asynchronous scheduler, but that will do for our examples. All right, so the leaf node. What the leaf node does is simply wraps a single computation f, that can be a lambda, a callable object, whatever you want, and it will expose execute, but won't make use of the scheduler. Because as an optimization, since the leaf node doesn't have any inherent parallelism inside it, we can just execute the computation on the current thread. And if a user really wants to schedule it, he can do it outside of the execution of leaf. And this is an example usage. We can construct a leaf node by simply passing any lambda, and then we can call .execute with a scheduler and passing a continuation to execute. So in this case, this will print hello world. There won't be any parallelism here. It's just a way of providing this building block for the futures. And if you're not familiar with C++17's class template argument deduction, the reason we can say leaf L without providing an explicit template parameter is because in 17, the class template parameter of leaf can be deduced by what you pass to the constructor. So this is a lifesaver for this particular design because it prevents me from having to write a ton of helper make leaf, make all functions. And this is the entire implementation of leaf. It fits on a slide, which is good, and it's not too complicated. So it's just a class that wraps an f, and if you were on Marshall's talk before, all we're doing is using the inheritance here to allow empty base optimization over f, which could be a stateless callable. And then what we do is we accept f by our value reference and move it inside the base class. So this constructor will allow us to provide the computation and also to deduce the template parameter thanks to the C++17 feature. Now we have the execute over here, which takes a scheduler but doesn't use it, so we don't give it a name, and takes the then continuation, which will be invoked sequentially after invoking f. So here what we do is invoke ourselves, assuming that f is a callable object, and then after invoking ourselves, we invoke the continuation. So the leaf node doesn't have anything special into it. It's just sequential execution of a computation plus a possible continuation. And this is an example of how class template argument deduction kind of works. So when you say this in C++17, the compiler kind of rewrites it for you to this line over here. So it automatically tries to deduce the template parameter of leaf by computing the type of the argument you're passing to the constructor. So if you haven't seen it before, it's kind of intuitive in the way it works, and it saves a lot of typing, and both for me and for you. So it's a really good feature. So the leaf node on its own is not really useful, but it is the smallest composable piece of the graph that we need to implement the other things. The first interesting node is sequence, which basically says, I will execute A and then B. So as I said, it takes two nodes as input, A and B, and the semantics of this node are that A is executed and then B is executed whenever A finishes. And remember that whenever A finishes can mean different things. For when any, for example, it means whenever the first computation of the node finishes. For when all, it means whenever all the computations in the node finish. So this needs to be robust enough to work with both, avoiding unnecessary blocking. So an example here is that we have two leaves, L0 and L1. One prints hello and one prints world. Then we can create a sequence node, passing L0 as the first argument and L1 as the second argument, and then execute it on a scheduler, providing some continuation, and this will print hello world with an exclamation mark. And all of this, because we're only using leaves, will still not make use of the scheduler because we don't need to. So this is the implementation of the sequence node. We have A and B as template parameters. We derive from both of them to make use of EBO. We have a constructor that moves A and B into the base classes. And the interesting bit is the implementation of execute. So what we want to express is execute A and pass the execution of B as the continuation of A's execution. And this is what we're doing here. First, we immediately execute A on the scheduler, and we pass this lambda over here as the then argument of A's execution. So we're saying, after you're done executing A on the scheduler, please invoke this lambda over here, which will capture the scheduler, capture our then execution, and will then invoke B execute on the scheduler, passing the continuation of the sequence node. So what we're basically doing is saying the continuation of the scheduler node, the continuation of the sequential node will be attached at the end of B. B will be attached at the end of A, and we will start the computation at the A node. Does that make sense to everyone? So the reason why we don't simply say A execute, semicolon, B execute, semicolon, is because, as I said, A might be a node that has inherent parallelism into it, like when any, and we want to continue executing B as soon as A is done. And the definition of done is different from nodes like when all and when any, because they have non-deterministic completion. Okay. So this is what I just said. A is immediately executed. The execution of B is passed as the then argument to A execute. And this allows us to have non-blocking asynchronous composition for two nodes. So this is the example we've seen before. And if we want to draw it as a diagram, we will have this sequence node containing the two leaves in place. The leaves contain the computations in place, and we are going to attach B to A through the then parameter and C to B through the then parameter of the leaf. So this is how we model this kind of chaining of computations. And this is an example of where having the asynchronous continuation between A and B is crucial. Because if you use leaves, it doesn't really matter. You could simply say A execute, B execute, and that would just work. But if you have something like any over here that has maybe 3 computations, and we want to continue as soon as one of them is done, in this case, maybe F2 is the first one to finish, then we want to continue immediately from F2 with our B node without waiting for F0 and F1 to complete. And this is why we need to provide the execution of B as a callback to A. Otherwise, we would have to block until every computation inside any is done, which is undesirable. Okay, any questions on the sequence node so far before we dive into the all node? Yes?
What would you use for work for that?
I don't use what?
When you pass event by capture.
On then? Yeah, theoretically, so if you want to be completely pedantic, what you would do is capture it either as an L value reference if it was an L value reference, or forward it if it was an R value reference or a constant value reference, but it doesn't really matter in this case. Like in a real library, you would be a little bit more pedantic. Okay, so the all node will be the first one to actively make use of the scheduler. It will take an arbitrary number of nodes as input, and those will be stored in a parameter pack fs. It will execute fs in parallel, and we will define completion of the all node as when all of the FS computations are completed. And remember that FS are other nodes, so we could nest when all, when any, or leaves, or sequential arbitrarily. So a usage example would be this one. We create a graph object of type all, and we instantiate it with 3 leaves, A0, A1, and A2. And then we execute the graph with some asynchronous scheduler, maybe something that detaches threads continuously. And at the end, we provide B0 to a CDAC out as the final continuation. And we have a sleep over here, which is a great engineering tool to make things like this work, which will prevent the graph object from going out of scope before all the computations are done. This is temporary. We're going to have a better solution later, but for now it works. And here, the output you will see is any order of A0, A1, and A2, and afterward it will have B0 that's guaranteed. Okay, so this is the way I decided to design it. The all node will store some state in place, and this state will contain an atomic counter of how many computations still need to finish. So if my all node has 3 leaves, the atomic counter will be initialized to 3, and the execution of every leaf will decrement the atomic counter by 1, and the last leaf to complete execution will be the one that triggers the continuation of the all node. So in this case, maybe A1 finishes first, it decrements the counter, reaches 2, doesn't do anything. Then A2 finishes, decrements the counter, reaches 1, doesn't do anything. A0 finishes, decrements the counter. The counter is now 0, so the execution of this leaf will be responsible for scheduling the execution of the continuation of the all node, which in this case will print B0. Make sense? So the node itself will contain this atomic counter initialized to the number of the computations, which we can retrieve by simply using size of ... operator. It will keep track of how many nodes need to complete the execution, and when it reaches 0, the then continuation of the entire all node will be executed. And every node in FS will decrement the counter upon completion. And again, we are using the sleep because we need to keep this alive until every node is finished. And we don't know when that happens because it's asynchronous. So this is the first part of the implementation. We just have the all class over here. It takes an arbitrary number of nodes and derives from all of them at the same time. It also has an atomic containing the number of the nodes. Note that we are not constructing the atomic here with size of ... because atomic construction is not atomic. I didn't know about that, but Thread Sanitizer did. And then we're gonna instantiate the node, moving all the children inside the base classes, and then we're gonna expose our execute function, which we're gonna see in the next slide. One thing that's interesting here is that inheritance is not just used for EBO here, but it also makes it really easy to work with FS as a pack, because we don't have to store inside a tuple and use std apply. We can just expand FS in place and do crazy stuff with it. Okay, so this is the crazy thing I was talking about. First of all, when we execute the leaf, the all node, the first thing to do is initialize the left counter to the number of nodes that need to be executed. And this is a store, so it will guarantee sequential ordering between this line and the rest of the code. Now we have this giant lambda here that we pass to scheduler. And as you can see, we have a ... over here and some parentheses. So this entire block of code over here is a fold expression over the comma operator that basically copy-pastes the executional scheduler for each computation that's in our FS pack. And you might be asking, where are we actually doing the expansion? The only thing we're expanding is the FS over here that's used to retrieve the base class that we want to execute from our cells. So this FS over here will be the first computation, second computation, third computation, and all this entire block will be copy-pasted multiple times to basically have that the execution on every type. Yes?
What happens if two of the FS are exactly the same type?
That's a good question. So if two of the FS are exactly the same type, then it will be ambiguous when you're trying to derive from them. It doesn't really happen in practice because they will be lambdas most of the times. But if you really wanted to make it work, what you could do is have a dummy wrapper type with a continuously increasing integer so that you create a dummy unique type for each one. So you can do that as well. But I haven't encountered it in practice. So, as I said, this entire thing is a fold expression over the COM operator. If you're not familiar with fold expressions, there are a new C++17 feature which basically allow you to generate code given a parameter pack. So they can fold a pack of ints into their sum, or they can just fold an execution of a function over the COM operator and simply generate code for you. And what we're doing here is invoking the scheduler, so potentially starting a new thread by passing a lambda that captures a bunch of things. So we capture this because we need access to the counter. We capture the scheduler because the nodes we're going to execute inside the all node might require the scheduler as well. And then we capture f by reference, where f is a static cast to the current type we're generating code for of ourselves. So this is the way we retrieve f0, f1, and f2 by simply casting ourselves to one of their base classes. And fs is a pack, and this whole thing will be expanded for each type inside fs. And then we copy then because we might need to use it as the continuation of the other functions. Now, inside every single execution of this lambda, the first thing we do is schedule the execution of one of the children. And we pass a continuation to that execution that when that particular child is done, will decrement the counter by 1, and if it was the last one, to decrement the counter. So if the counter is now 0, then that child will be responsible for the invocation of the then continuation of the all node, so of the one we captured over here. Any questions so far? Yes?
Why the outer call to scheduler?
Sorry?
You have an outer call to scheduler.
This one?
Yeah, why that one?
Because, so we have this call over here because we are in the all node, right? And the semantics of the all node say that we are going to execute all of these computations potentially in parallel. So if the scheduler is something that just spawns a new thread, this is where we want to execute, this is where we want to spawn the threads, one per each computation in the all node. Doesn't make sense. So the invocation of scheduler can literally be run this on a new thread. Okay? So is everyone clear on this? Feel free to ask questions and clarification. Okay. So this is an example expansion for two hypothetical A and B nodes. Size of ... fs will expand to 2 because that's the number of types in the parameter pack. And then we will have two expansions of this giant scheduler thing separated by a comma, because this is what the fold expression does for us. It just expands and puts a comma in between where required. The first expansion will capture A by simply static casting to the type of A, which is one of our base classes. The second one will capture B in the same way, and then we will execute A, execute B, and both of them will have the same body. And this probably makes it clear why we need the scheduler, because we want to execute both of these things in parallel, so we want to schedule both of them on separate threads. And since the left counter is atomic, it is guaranteed that only one of them will see the counter as 0, and only one of them will execute the then continuation of the all node. So far, we have three abstractions. We have leaf, that just wraps a single computation into a node and allows composition. We have sequential, that executes A and then B asynchronously. And then we have all, that executes a bunch of computations in parallel. And with these tools, we can already model arbitrary fork-and-join computations. So we could have something like, given A0, spawn B0, B1, and B2 in parallel, and when all of them are done, then execute C0. So a very simple fork-and-join. And the way we would write that is something along the lines of this, which is super pretty, I know. So if we read this in the right order, we can see that we have a leaf over here that prints out A0, which is the first argument of a sequential node, and the second argument of the same sequential node will be the all node over here that spawns B0, B1, and B2, and all of this is the first argument to the sequential node that will eventually spawn C0, which is the last computation. And this basically models the graph we've seen on the previous slide. So we can do this, but so far we haven't been able to pass any return value or accept any input value, which is quite defeats the purpose of futures. So we will deal with that next before looking into any. Any other question on the all node? Yes?
Have you considered overloading operator arrow sequential?
I haven't considered overloading operator arrow. I don't think that will work because it has to take return a pointer, so I struggle to see how that would work, but we're going to have a .then, which basically achieves the same purpose without overloading operator arrow. Just less fun, but it works. So now we're going to deal with return value propagation. And this is going to be a little bit tricky, but let's begin by looking at leaf node and understanding that the execution of any graph always begins from a leaf node. It doesn't matter if you have a when all, it doesn't matter if you have a sequential. Eventually, you're going to start somewhere, and you're going to dive deep into those nodes, find a leaf, and start from there. So the leaf node is kind of special in the case that you must be able to produce and accept values, and it needs to know what value it's going to accept at the beginning, because it's going to be the first one to be executed. And composition nodes such as sequence and all must be aware of what the values their children are producing, and since they are part of the same type, they can do that, and they can deduce what value they can output by simply computing the decal type of whatever computation they have invoked with the children's return type. And everything obviously can be encoded as part of the node type. So we're going to extend our node concept to have an in type and out type aliases. And in this case, for leaf, we're also adding a new template parameter that tells us what the leaf will take as an input. Since the leaf can be the first one to start the execution of the graph, we need to tell the leaf, OK, we're going to give you an int, and then you're going to do something on that int. So this is the only place where the user has to manually specify what will be given to the graph. And the out type over here can simply be deduced by computing the result of calling f with the in type. Now that we have this, we have a problem, because we are relying on class template argument deduction to make it easy to use and nice to look at. However, class template argument deduction doesn't work partially. It must deduce all of the parameters. Fortunately, since this is a very common use case, what was added alongside class template argument deduction is a new feature called a deduction guide that allows you to tell the compiler in which way you want parameters to be deduced from a constructor invocation. And this is what you see over here. The syntax is kind of weird if you haven't seen it before. It just looks like a constructor, but it has no body. You simply specify a type that you want to be deduced by using an arrow, such as the trailing return types in auto functions. And in this case, what I'm saying here is that I want my constructor to simply take one lambda of type f. And I want you to deduce the type of leaf, where the input type is going to be deduced by looking at the operator of this lambda. So it's going to basically look at how the operator of the lambda is laid out and extract the input type of the lambda. And the type of the computation is going to be f decayed, because in this case we're taking by forwarding reference, so we want to get rid of any const and reference. And the way I'm extracting the argument type of the lambda is by using Boost Callable traits, which was recently added into Boost, and it's an amazing library that just allows you to inspect various properties of callable objects, such as their arity, the parameter types, whether or not they are lambdas, function pointers. And this works with all the abominable types, such as volatile callables or volatile const callables, so you don't have to copy-paste all that code yourself. So what I'm doing here is simply saying, okay, I want to get the argument that the lambda accepts, and I want you, compiler, to deduce it as the in template parameter of the leaf. After we do that, we can simply instantiate things in a quite clean way. We can say, I want a leaf with this lambda that accepts an int, and this will be deduced for us as a leaf taking an int and the type of the lambda as the second template parameter. Or we can have a leaf taking an std string, and this will be deduced as a leaf taking an std string and having the lambda as the second template parameter. A caveat is that you cannot provide an overload set to a leaf or a template because you cannot extract the information about the parameter you want from those entities, as you cannot take the address of an overload or of the address of a template. But that doesn't really matter because you need concrete type information in this case when you're building the graph. So it wouldn't make sense to pass one of those. So this solves the problem quite elegantly. Now that we solved this deduction issue, we need to fix our execute. So this is what it looked before. We have a call to this, which is the computation we're storing in the leaf, and then we're invoking the then continuation afterwards. However, now the computation we're storing in the leaf might take an argument. So we need to pass something into here. And we don't really have anything we can pass from this signature, so we need to expand our node concept by adding a new argument into execute. And the argument will simply be an input taken by forwarding reference. And the way we will use it, we will provide it as the argument of the disk computation over here. And then the result of the computation inside the leaf will be forwarded to the then continuation of the leaf. So this allows you to basically wire input and output of nodes by using simple return types. And this works easily with the leaf because we have no concurrent execution, so we can just implement composition as normal function composition in C++. So as an example, here we have a leaf that takes an int x and returns x multiplied by 2. And what we do when we execute it, we provide an input as an argument, 21, which will be passed over here. Then the input will be passed to the invocation of the leaf. So it will go in this x over here. It will be multiplied by 2. It will result in 42. So the value 42 will then be passed to the then continuation, which in this case will take an int and print it out to a ctc out. So the execution of this graph over here will print out 42 by going through the leaf and then the continuation. Make sense? Okay, so this is the final implementation of leaf. It's a little bit bigger. It still fits on a slide, surprisingly. And all we have added is the new input parameter over here. We've changed the way we invoke the current computation and then. And also we added this deduction guide over here that allows us to deduce the type of in from the operator of the callable object we're passing. And finally, we also have the in type and out type, which we will have in every node that simply inform us about what input we're getting and what we're producing. So all the other node types will require the same modifications. They will need to expose in type and out type. They will need to accept an input argument in execute. They will have to execute the children by passing input to their execution method. And then they will need to invoke the then continuation by propagating the result of the previous operation. Let's apply these changes to the sequential node now. So the sequential node, if you remember, just takes two template arguments, A and B. We don't need to add any in argument here because it can be deduced from the children nodes. And in this case, the input of a sequential node is the input of the A computation. And the output of a sequential node is the output of the B computation. So this is very simple. If you look at the diagram over here, imagine we have a sequential node that has two leaves. The first one returns 42. The second one accepts an int and returns that int converted to a string. So the first leaf will take void as an input and int as an output. And the second leaf will take int as an input and string as an output. So if we want to move this one layer up, the sequential node will take void as an input and string as an output. And internally, it will do the transformation by calling the children nodes. So this was the execute call for sequential before, where we basically just provided the execution of B as a continuation of A. Now, we don't change the structure at all. It's exactly the same thing, but what we do is provide an input parameter over here, which will be forwarded to the execution of A over here. By the way, this is just a macro that expands to a CD forward, because I'm lazy. And then we're gonna have our lambda continuation accepting a result, which can be generated from the execution of A, and that result will be forwarded as the input of B's execution. So this is how we do the wiring between A and B. This input will be transformed by A execute. The result of the transformation will be given to this continuation over here, and that result will be passed forward to the execution of B. So this is how we pipe them together. Any question on this? Clear to everybody? Okay. So again, this is a usage example. You can have a sequential node with two leaves. This is what we're seeing in the diagram. And then execute them by passing some value. And in this case, 21 will be passed here first, multiplied by 2. The result will be propagated to the second leaf, converted to string, and then the string will be sent to the continuation of the graph, accepted here as hex, and then it will be printed out to SDC out. So this will print 42. And again, we don't have any parallelism here, any usage of the scheduler. Everything is known at compile time, so this will very likely just be a single call to SDC out, completely inlined by any compiler. And this is the final implementation of the sequential node. Any questions on this node? Yes?
So I guess it's not final because it doesn't have a void.
Yes. So void is a pain. And I have a slide on that. I'll get to it. So leaf and sequential now support asynchronous propagation of values. All is a little bit more complicated. So multiple parallel continuations need access to the input at the same time. Because if all is getting an input, you will have multiple parallel computations that are reading the same input. And you cannot really pass it directly when you're calling execute, because the stack frame of the execute call for all might be removed while the computations are still going forward, because they are executed asynchronously. So what you could do is either copy the value on each computation and give every thread its own copy, but that might be expensive depending on the type of the value. Or, we have this shared state inside the all node itself, so we can just store the value inside the all node itself and give a reference to that value to every computation. And this is what we're going to do in this implementation. Okay, so about void. Maybe I removed the slide, I don't remember. But void is really difficult to deal with because it's not a regular type. There are proposals to fix that. I don't think that we will have that anytime soon. So what I do is create an empty nothing type and then use some crazy template magic to detect void and automatically convert it to nothing. And I do that both when producing and consuming, so that it's completely transparent to the user, but underneath is doing a lot of transformations. It's quite annoying. Okay, so this was what I was talking about with all. If we accept an input parameter in all, and then simply give a reference to each computation that will be executed synchronously, what happens is that we have no guarantee that all the computations will be done before we reach the end of this closing brace. So if we do that, the computations will store a reference to an input that was on the stack but now doesn't exist anymore. So we cannot do that. In this case, they will try to access a dangling reference. So what we have to do is either copy the value or store it in a place where it's going to be guaranteed to outlive all the computations that run in parallel. Make sense? So what we do is this. We have our all node. It contains the leaves, whatever, the atomic counter. And alongside the atomic counter, it will contain the input. So what we do is we accept the input from our parent. We store it into ourselves. And then since we are guaranteed to live long enough for our computations to complete, we just provide a reference to that to our leaves. And we're going to get to that. Before it, we need to compute the in type and out type. This is going to be, again, quite simple. The in type will be basically the same as what all our children nodes take. So since our children nodes need to have the same input type, because it will be executed on the same input, then what we can do is simply compute a common type T of all the in types of our children nodes. This is how we do it. The output type, however, we want to aggregate the result of each node that can potentially have a different type. So an easy way of doing that is by just sticking all of them inside an STD tuple, so we can expand the children's out type inside the STD tuple, and it will give us the correct return value for multiple computations. And if we see the diagram here, you can imagine that we have a bunch of leaves. They all take int as an input, so the input of all will be int. And the first one returns an int, second one returns a char, and the third one returns a float. So the output of all will be a tuple of int, char, and float that we can access when all of them are done. So disclaimer, this is different from how futures work. I just prefer this kind of design. I also don't handle exceptions or anything like that. So if you want to propagate an error, you will have to encode it in the type system with this design. But it is a future direction to explore. So now we have the share state thing. And instead of having them as data members, what we can do is just encapsulate them inside the share state inner class, which will contain the input, as we want to cache it for our computations, and the atomic counter that counts how many computations are left. And then we simply provide a constructor that forwards the input inside our input cache over here, and initializes the atomic with the number of computations atomically. So this is how it looks like. We have the in type, out type, the share state, and then we have some aligned storage for the share state, because we don't want to force the input type to be default constructible. So we're just going to have some aligned storage and control construction and destruction manually. And then we're going to have an out type instance, which is the final tuple, that will store the values produced by the computations. And this will be accessible from the children of the all node. So the idea is that now that we have this aligned storage over here, we are in charge of controlling the construction and destruction of the share state. And what we can do is constructing it when we call execute, and destroy it when the last node is done. So we're kind of implementing a share pointer on the stack where we manually control construction and destruction. So the new execute will have to do this. First of all, it will construct the state by taking the input from our parent and putting it inside the state. So we are storing it in a safe place that will live long enough so that our children nodes can access asynchronously. Then it will have to schedule the children nodes, and we've seen how to do that with the default expression, so we're going to basically generate code for each node. Then on each completion of the nodes, we will have to fill one of the elements inside the tuple with the result of the particular node. And finally, the last node to complete will have to invoke the then continuation and also destroy the state to correctly invoke the destructor of the input, which might have side effects. So now we have a problem here. And the problem is this line over here. We need to fill values with each node's result. So folding over the type is not enough anymore. We actually need to know the index for which we want to, with which we want to access the tuple at. And we will have to replace our beautiful fold expression with something a little bit more powerful that allows us to also know about the index of the iteration at compile time. So one way we could do that is by having this magic enumerate types function. And I use the word enumerate because if you're familiar with Python and other arrangers library, enumerate just simply zips a sequence with its index. And what it does is, given a bunch of types as a template parameter, it will invoke this lambda over here, passing an integral constant, storing the current index of the iteration at compile time as the first argument. And the second argument will be some t empty type that allows us to retrieve the current type as well. So it's just a type wrapper. And the idea is that this models a compile time for loop over all the types where you can retrieve the index and the type at compile time. So once we have that, what we can do is we enumerate over all the types, and then we schedule every computation as before, either on a new thread or whatever kind of scheduler you're using. We are still going to capture one of the base classes, depending on the type we're iterating upon. The only difference is that we don't have the type name here anymore, so we need to unwrap it from the T type wrapper that we're passing from enumerate types. And this is basically just accessing the colon type member of the wrapper. And we cast ourselves to that type, which is one of our base classes, and we capture that as a reference. So in this case, for each iteration of the for compile time loop, f evaluates to this, casted to the type of fs we're iterating over. Now, what we do, we execute f as before, and as the input, we pass the input that we stored in the state over here. And that is guaranteed to live long enough to make this work with any kind of scheduler. And then what we do is provide a continuation that will accept the output of the current computation, and in here, we will have to store that inside the tuple. To do that, what we're doing is invoking std_get on the index that's given to us from enumerate types. So this I over here encodes the index in a way that's accessible at compile time. And in this case, it's just an std integral constant. So what we do is we get the type of I and immediately instantiate it afterwards so that it can be a constant expression. And this will be 0, 1, 2, whatever. So we access the right spot in the tuple, and then we assign the result value by forwarding it into that spot. Yes, 1 second. Afterwards, what we do is simply decrement the counter by 1. And if we are the last ones to do that, we destroy the state, because now it doesn't need to live anymore. We can invoke all the destructors. And then we invoke the continuation of the all node by moving the output tuple into it. Yes, you had a question?
Is that, so if you've got, say, bytes in that tuple?
If you had what, sorry?
If you had bytes, if your return types were bytes, is that guaranteed to be safe writing the two parts?
Okay, the question is, if you add bytes as the output types of your computations, would this be guaranteed to be thread safe? In my real implementation, what I have is a cache-aligned tuple. So each element is aligned on a cache line boundary to avoid false sharing. So that would be probably enough to prevent that. And I asked this question, I think, 1 year ago on Stack Overflow with the language lawyer tag, trying to understand if tuple is guaranteed to be thread safe when multiple threads are accessing different members of the same type. I don't think there is any explicit wording in the standard that guarantees that. So if your type is small enough, then you could probably have issues. So it's a good idea, both for performance and safety, to pad these things out. Any other questions or comment on this? Detlef?
I believe it should be safe if you actually access different elements of a tuple from different threads. That should be safe, as long as it's not a bit field.
Okay, that's interesting. So Detlef's comment was that it should be safe to access different tuple elements from different threads as long as the elements are not bit fields, because then you might have bit races. Well, the real answer is don't return bytes from your computation. Return something useful. Any other question on this? Does everybody? Marshall?
Lisa and I were just discussing Detlef's comment, and remembering what Jonathan said earlier today about bit fields not having types, it would be hard to. We don't see how you could actually put a bit field in a tuple.
Yeah.
Okay. The comment was, there probably is no way of putting a bit field in a tuple. Any other comment or question? Are we all on the same page? Do we all understand what's happening here? Kind of. Okay. So how much time do I have left? This is a usage example. We can create an all node with multiple leaves. In this case, they're all going to take an int and return x, x plus 1, x plus 2. And this is all part of the all node. And then we're going to sequentially compose the execution of this all node with another leaf that accepts a tuple of int, 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 and is going to simply return the sum of the first element, second element, and third element. And if we invoke this with 0, what's going to happen is that we're going to return 0 plus 1, 0 plus 2. And when all of this is done in parallel, we are going to invoke this leaf over here, which will return 0 plus 1 plus 2. And that result is going to be passed to the continuation, and it's going to print out 3. So that's how it works. So quick recap. The all node stores both the counter and the input in place inside its share state, which is constructed when we call execute and destroyed when the last computation is done. So we're using aligned storage here. The output values are stored in a tuple, which again lives in place inside the node, but is not part of the share state because the children must be able to access it after the last computation is done. And we fill it by enumerating fs as compile time, having an index and a type, and just filling the tuple in. And the last computation to finish will invoke the then continuation of the all node by moving the tuple into it. Also, what I do in my real library is apply an optimization. When we are enumerating fs, we can avoid scheduling one of the computations and just run it on the current thread instead of doing nothing on the current thread. So that avoids us from wasting one thread or whatever your executor is providing. And the way you can do that is by simply having if const expr I equals 0, then invoke it without going through the scheduler. So this is what I was saying before about void. I have a special type called nothing, and I convert void to nothing in order to make everything work. It's just a bunch of template horrible magic. We won't cover it. We will pretend that void doesn't exist. So another main issue we had before is that we had to use sleep in order to prevent this thing from going out of scope. So can we do any better? We can, and it's not that hard. What we're going to use is a latch. Is everyone familiar with the concept of a latch? Okay, so a latch is basically a counter plus a condition variable plus a mutex, and you can wait on the latch, so block the current thread of execution until the counter reaches 0. And the latch allows you to decrement the counter from any other thread in a safe manner and will notify the waiting thread when that happens. So you will have this latch, for example, over here, that's initialized to 3. Then you can safely spawn 3 threads that concurrently count down on the latch, and you can wait on the main thread, which will block until the counter is 0. And this code over here is guaranteed to eventually unblock when all of the 3 threads are done and basically invoked countdown on the latch. So this is what it is. It's just a counter that allows you to synchronize a thread with other threads. It's safe and easy to use. And I think it's part of the concurrency TS, but you have an implementation in Boost as well. So what we're going to do is create a new abstraction that, given a graph, it will run it, and it will block the current thread until the graph is completely finished. We will call this sync execute. It will take a scheduler, a graph, and a continuation. What it will do is create a latch with 1. So it's just going to wait for a single countdown call. It will wait at the end of the scope. So sync execute won't reach the end of the scope until the latch has been decremented. And what we're going to do is invoke the graph execute, passing the scheduler as an argument, nothing as an input, and the continuation of the entire graph. So the then continuation of the entire graph will be responsible for executing the continuation provided by the user and also counting down on the latch. So this means that the latch is guaranteed to wait until we hit this countdown call over here, which is the continuation of the entire graph. So this means that we won't be able to go out of scope until the entire graph is completed. And this will be an elegant way of allowing you to say, I want to execute this graph and wait until it's completed. Does that make sense?
Why would you want to do that?
Well, why would you want to do that? Well, eventually you have to block somewhere in your program, maybe. In the case of testing, for example, I want to run a graph and then obtain the result and make sure it's correct. I need to eventually block because I don't want to go outside main before the graph is completed. Does that answer your question? So what's the alternative?
If you have a perfectly good thread around, why don't you use it?
A perfect what?
Perfectly good thread around, why don't you use it?
Well, we are using the thread, but eventually, you know, I'm gonna have this graph. I'm gonna fan out in my executor. I'm gonna have whatever threads I want. But at the end of this big computation, I want to make sure that I'm able to finish, right? So eventually, there has to be a place where I block. Detlef.
Well, I agree. Somewhere you simply have to block and design a place. This is the place, and where you set up the whole graph might actually be a good place. If you don't have any, it might be an option to move everything into the continuations.
Mm-hmm.
So after you actually have started, your graph is actually an empty graph, so you can throw it away. And the last, and then you only have the state inside of the node that has a state of the part of the graph that is for this continuation and for the thing that is feeding into it.
Okay, I'm not going to repeat that, but that's...
But with any, that gets complicated.
Yes. So one thing I want to point out is that this thread is not wasted because, as you remember, we only use the scheduler when we have to. So even in the case of when all, for example, this thread in my real implementation will execute one of the computations on that thread. So we only schedule when we actually need to. So this thread will actually do work. It's not completely wasted. Oh, sorry, yes.
So I just wanted to point out that probably it's not always the good idea to kind of not schedule a thing, because your continuation you may expect to be executed on the scheduler I asked it to be executed on. When I was passing it, I was like, well, I know where it's working, so I have this memory here, I know how to access it. Like there are complicated examples where it can be a problem that you just threw away my scheduler, which I carefully busting as an argument. So it's probably not the best thing yet. About the synchronous execute, I think, if I'm understanding correctly, that you can just, if you don't want to block, you will just allocate graph on the heap. And then you'll just call, like, schedule essentially, like call graph execute on an asynchronous scheduler and just capture the shared
You can do that. My point is that eventually you're going to reach the end of the program, right? And you want that to be...
No, because I have a network service. There is no end of my program. I can start...
Sure, okay, yeah. In that particular case, yes. If you're like a real-time, long-running service, then sure, you can do something like that. You can store the whole thing on the heap and let it finish, like detaching the whole graph. Yeah, so one comment which is important is that I use the avoid a scheduler for some computation as an optimization, but sometimes you don't want to do that, so you might want to force it to be executed on the scheduler because your executor might be doing something different. In the case of simply detaching a thread, that's a viable optimization, but a proper library would allow you to control whether or not you want that to be enabled. Okay, so this is a user example. It's exactly the same thing as before. I don't have much time, so I'm not going to go step by step. The only difference is that we use sync execute over here, and we're guaranteed that the graph will live in scope long enough for everything to be executed. And this is the continuation style syntax. So which one is better in your opinion, the first one or the second one? Does anyone think the first one is better? So yeah, until we can call a function with curly braces, maybe uniform functional call syntax, we will have to mix curlies and parentheses in order to have this kind of syntax. And what we're doing is basically providing syntactic sugar to generate the type that you see above from this chain of .then calls, which makes it easier to read because it's left to right. So to achieve this, what we do is add a then member function to every node type. And this then member function that you can see over here is a template member function. We return auto. And it will take an arbitrary object x, which can either be a node or not a node. If x is a node, then will return a sequential node, moving myself as the first argument of the sequential node and continuing with x. If it's not a node, then it will return a sequential node, moving myself as the first argument of the sequential node and wrapping x into a leaf. So what this allows you to do is provide a lambda without having to wrap it into a leaf yourself. It's just going to do it for you. And the way it works is that we basically detect whether x exposes a .execute method. If it does, we know it's a node, so we simply return a sequential node by moving this and x. If it doesn't, we're going to assume that it's a callable object, and what we're going to do is simply wrap into a leaf for you, so you don't have to do it yourself. And we're using if const expr, which is quite nice. Is executable is just a trait that uses the detection idiom to detect whether or not x exposes execute. And this is a usage example. We have a leaf, returns 10. Then we add a continuation. Given then we want to multiply by 2. And then we have another continuation that uses an all node. So we say, after multiplying by 2, I want to execute these two things in parallel. And those are going to be two leaves, adding 5 and removing 5. And then we have a final continuation that sums the results together. And it's way nicer than nesting a lot of sequential nodes. OK, so I have 10 minutes to talk about the any node and show you some benchmarks. I'm going to go quick on the any node, which is not a good idea because it's the most complicated one, but I hope you can get the idea of how it works. So the any node takes a bunch of computations as input, and as soon as any of them is completed, it has to invoke the then continuation, because we don't want to block until all of them are done. And in this current implementation, I don't have automatic cancellation, so the remaining computations will still run in the background, but they won't prevent you from executing your desired continuation as soon as possible. So this is not optimal. The user can implement cancellation themselves, but eventually the library should do that for them. And the issue here is that since we're running stuff in the background, even though we already are completed, we cannot know when we can safely destroy graph. So if we want to use our previous latch solution, it will not work because we will unblock the latch before the computations that are running in the background are actually done. So we need to do something a little bit smarter there. And this is how it works. You instantiate exactly the same as the all node, providing any number of nodes. And internally, any will have a state containing an atomic counter, we need that, and the input type and the output type. So it's exactly the same as all so far. The difference is in what we are returning. In the case of all, we return a tuple because we want all of the values aggregated in the same place. In case of any, we're just going to get one of the values. So the type that models that is variant. We are going to return a variant of the output type of every node. So in this case, imagine we have this any over here. It has leaf that returns an int, leaf that returns a float, and leaf that returns a char. The final output of any will be a variant of int, float, and char, which will basically allow you to get the result and also know where it was coming from. So the share state is exactly the same. We have the same state and the same aligned storage and out type, so it's exactly the same as all. The interesting bit is what happens in execute, because now we kind of have two execution paths. We have the execution path that is the completion of the graph that calls .then, 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 but that execution path might be finished before the other computations in the background are. So we need to keep track of those two paths, the any that we actually chose to go forward with, and the other computations at any that might still be running in the background in order to provide deterministic blocking of the graph. And a way we could do that is by having two continuations. We have the then continuation, which allows you to propagate the result forward and do something with it, and the cleanup continuation, which tells you when the tasks running in the background for which you don't care about because they are the one you didn't choose when executing the any node will be done. So for leaf, sequence, and all, cleanup is the same as completion. So there is nothing different there because we deterministically know that when all of them are done, we can remove the node. So there is no difference between then and cleanup. However, for any, then will be invoked for the first computation and cleanup will be invoked for the last computation. So cleanup is just a way of allowing us to basically reference count on all the any nodes in the graph and destroy the graph when everything is done, even though we are discarding its result. So this might not be the same if I had automatic cancellation, but in the current design, this is what I do. So what we do is propagate cleanup forward in all the execute calls. And here you can see in the any implementation of execute, for each computation f inside any, we will decrement the atomic counter. Then if we are the first one to decrement the atomic counter, then we will move our own result value into the values variant and invoke the computation, if we are the first one. If we are the last one, then we will destroy the state, so we will clean up after ourselves and inform the rest of the graph that we are actually done by invoking the cleanup continuation. So in this case, we have the completion condition, which is, am I the first node to finish? And the cleanup condition, which is, am I the last node to finish? And we keep track of those two paths and keep going with them forward. So this is the entire implementation. And the way we can now implement sync execute is by counting how many any nodes are in our graph by basically recursing over every children and counting the number of any nodes, which are the non-deterministic ones, adding one for the entire graph as a whole, and then in our execute call on the graph, our then continuation will count down on the latch, and our cleanup continuation will count down on the latch. So the point is that every any node will call cleanup when it's done, and then when it's completed. And if we have 3 any nodes, we're expecting 3 countdown calls on the latch, plus 1 for the final continuation of the graph. And this is how we can block deterministically. So this is kind of a diagram of how it works. So we begin with the graph itself, which is called F0, and it increments, it basically gives us a +1 on the latch that we need to care about. Then F0 maybe spawns an A0 and A1 in parallel, which spawn an any, another any in parallel. And since any is one of those non-deterministic nodes, we need to keep track of those as well. So we're going to have +1 and +1 over here. So our latch will be initialized to 3. Now, the colored path is the success path. So it's the path we're taking to produce the final result. In this case, B0 finished before B1, and C1 finished before C0. So we are aggregating the results from B0 and C1 and passing them to the final then continuation, and this is where we decrement the counter by 1. So this is the final state of our graph, and it might happen before or after the cleanup. We don't know. And now we still need to wait on 2 cleanup calls, which will be eventually executed by the paths we didn't take on the any nodes. And the first cleanup will be -1, the second cleanup will be -1, and this will allow us to destroy the graph whenever everything is done. So we're kind of reference counting the non-deterministic execution paths of any, and we are destroying the graph when we can. Any question on this? Okay, let's get to the interesting bit. I have 5 minutes. Some runtime benchmarks against Boost Future. So what I tried to do here is model an I/O-bound computation and computation graph, so with various continuations. And I use different times for the computation. So for example, I'm simulating an I/O-bound computation that takes 0 milliseconds, one that takes 1 millisecond, one that takes 10 milliseconds. And I wanted to measure when it's beneficial to use this system compared to what Boost Future gives you. So as an example, if your computation, your I/O-bound computation takes 10 milliseconds, then the difference is very, very small. So you won't likely benefit from this. The added complexity is not worth it. But it is worth it if your computation is very short-lived, because it can be twice as fast as Boost Future. This is the case of a single node. So it's simply just instantiating a node and invoking it and waiting until it's done. And as you can see here, if we use Horizonte, which is the name of the library that contains these abstractions, you have a huge difference with Boost Future. And this was measured by running this 1,000 times in a loop and getting the average. And the conclusion here, if you have a single node and your computation takes between 0.1 milliseconds and 1 millisecond, and you're doing this over and over in a loop, then you will benefit from using this kind of design with a dynamic allocation and type erasure. However, if it takes more time, then you shouldn't bother, because the overhead of dynamic allocation and type erasure is minimal compared to the computation time. Yes?
What kind of scheduler did you use?
I use a detached scheduler and a thread pool scheduler. With Boost, I always use the detached scheduler, though, because I couldn't find a way of passing an executor. So in this case, if you see there are 2 lines, green and yellow, which are the detached scheduler and pool scheduler. And Boost Future always uses the default scheduler, which I looked at the implementation is just calling detach, so it's the same thing. Now, the interesting part is, if you keep adding continuations like .NA, .NB, .NC, then you can see that Boost Future scales linearly. So the more computations you add, the more overhead it takes. And since we are not doing anything fancy here, all that overhead comes from the dynamic allocation and type erasure. And as you can see, if you have a complicated graph like .NB, .NC, then you still have this threshold around 1 millisecond for your task, where it doesn't really matter what you use. But before, if you have some computation that takes 0.1 milliseconds, the difference between the non-type erased version and the type erased version gets bigger and bigger. So if you have some sort of thing that you want to represent as a nice abstraction over parallel computations, and you're going to run it often in a tight loop, then you will benefit from using this kind of system. Now you can go crazy, and you can have a B, C, D, E, F, G, H, so this kind of linear chain. And to be a little bit more fair to Boost Future, I also tried the deferred execution policy over here, which will not spawn unnecessary threads if you have to, which is closer to what my implementation does. And you can see if you use normal Boost Future, scheduling everything asynchronously, you will have a huge difference for a small computation. Imagine your computation takes around 0.05 milliseconds, you will pay 0.6 milliseconds just to execute it. And that's all overhead of type erasure and dynamic allocation. If you go with the deferred method, which prevents the creation of unnecessary threads, you will have a huge time save, but still you have a gap over here that's caused by the type erasure and dynamic allocation of the future objects themselves. So in the end, the conclusion is always the same, but when you have a lot of chaining, even with computations that take 1 millisecond, then you have a gap over here, which might be significant if you're running this in a tight loop. Then I went a little bit wild. I tried with all. And with all, you can see that there is a difference between using the detached scheduler and the pool scheduler, because this is where we're actually creating new threads for the computations. Then I tried with any, and it's very similar to all. Then something a little bit more complicated, maybe an any of a computation that has a continuation, that has an all, and then everything has a then as well. And the results are always very similar. Around the 1 millisecond threshold, the difference stops being significant, but before that, it's always quite faster than Boost Future with the default executor. And the conclusion is that if you have a very short-lived task, it doesn't take long to execute, and you're doing that over and over, then avoiding the overhead of type erasure and dynamic allocation can be beneficial. So the library is available here on my GitHub page. Is work in progress, is not really ready for anything. It was just experimental, and I'll probably continue working on it and see if I can figure out a use case for where this can actually be applied in a real system. And one of my conclusions is that expression templates can be applied to pretty much anything. You usually think about them in terms of mathematics, like matrix multiplication or figuring out automatic derivation, but it's just a way of encoding steps in a type system. You can do it with future, and I'm sure we can find other crazy application of this technique. And sanitizers are invaluable, especially thread sanitizer. I've ripped my hair out multiple times trying to figure out why something had a very weird data race that happened once in a blue moon, but thread sanitizer always was right and told me where to look at. It's really great. And C++17 features greatly simplified implementation. Things like class template argument deduction, fold expressions, and even minor things like if const expr, they can really make the implementation of something that's very reliant on templates easy to read and easy to write. So it's not just a minor feature upgrade for me from 14, because if you are doing library development and writing a lot of code that requires templates and stuff like that, it really makes your life easier. So as some future direction and ideas, I want to look into automatic cancellation in any nodes. I have some ideas, but I haven't played with that yet. And a composable type erasing wrapper, because maybe you want to have this graph, part of the shape of the graph at compile time, then you have that, you type erase the whole thing, and then you move that around. And that would be useful if you don't know how to compose multiple pieces of the graph, but those pieces themselves have a shape that's not at compile time. And then maybe look into exception handling and basically providing an automatic failure path. That could just be a variant of value and an exception hidden between an ISO interface so that the user doesn't have to care. So that's pretty much it. Thank you. Hope you find it interesting. So if you have any question, feel free to ask or find me afterwards. Yes?
How complicated could you make it full compiler though?
I have to say, I didn't have a single internal compiler error while implementing this. That's very surprising. And both GCC 7 and Clang 8 were fine with my implementation. So the compilers were actually well behaved this time. Didn't have much to complain about. I think I filed one bug report, but that's it, which is pretty good. Okay, so that's a different point. I haven't tried stressing out compilation in terms of applying 1 million continuations. I'm sure that it will either fail or just be so long that it becomes unpractical. Yes?
Did you look at scalability?
Sorry?
Scalability.
In scalability at runtime or compile time?
No, scalability as a number of bytes.
So,
0, 1, 2.
yeah, sure, okay. In this case, I don't think there is any different from the idea of boost future or STD future itself. So you will benefit from having multiple threads only when you are able to do multiple parts of the graphs in parallel. So if you have an any node or an all node that takes 20 different computations, then if you have 20 available threads, it will benefit from it. However, if you don't have anything like that, then it doesn't really scale with the number of threads. In my what? In my benchmarks. So I did my benchmarks with my laptop. It has 8 threads, I think 4 physical and 8 logical.
And you had your pool size was basically 8.
Yes, that's it, yeah.
One of the major issues you'll be facing is the fact that your bottleneck on is the fact that we're not on data bus.
Yes. So, I think this is a more general problem, not with this particular implementation, but with futures in general. And they are not really the abstraction to express linear scalability or anything like that. They're more a way of telling you, I have these multiple computations and I have this shape that I want them to be executed in. And then those individual computations might be making use of a linearly scalable algorithm. But I don't think that we can do better here. It's. I'm slightly familiar with it, but not enough to say that I'm experienced with it.
Because, for example, lots of what you did there was about Baker's scheduling.
Mm-hmm.
Essentially, what you do is you say, if I've got a number of tasks, I won't bother supporting on separate threads. I'll just group them as one and run them on one.
Yes. So this is actually happening in my implementation, because if you remember, the sequential node doesn't use the scheduler.
It's called Baker's scheduling.
Okay. Yeah. Any other question? Yes.
What is the use case what you were trying to solve?
I'll be honest, I did this mostly for experimentation and fun, and the conclusion I got from it is that if you have a use case where you have a computation that's being run multiple times in a title loop, and that particular computation takes, as you see from the graphs, less than 1 millisecond or some other threshold depending on your machine, and you still want to use the abstraction power of future composition and not schedule things yourself manually, then this would be a useful tool. In all honesty, I haven't thought of a realistic use case for it yet. There was more template fun. Okay, thank you.